All right, thank you so much, Karthik. Yeah, unfortunately, my student couldn't make it because of some visa issues, so he asked me to give this presentation on his behalf. And Faisal is a PhD student working on nucleation seeding, and we're showing today some results. How can you enhance strength and porosity with these systems? All right, so we're going to start with a general introduction. I know there's a lot of young students here, and the best way to communicate with young students is through memes. So I'm going to start with a meme here. This one right here I really like. And how does it correlate with what we are going to talk about? Well, you could have your partner thinking, I bet he's thinking about other women, but you're thinking, well, what can I do about the early strength of my low carbon concrete? And I should be very clear here when I say low carbon concrete, I'm talking about concrete mixes with high amount of SCMs, high amount of fly ash, slag, natural pozzolans, clays, whatever you have. When you dilute the clinker to 40, 50% or more, your early strength starts to suffer, and you have to find solutions for that. And one of the obvious solutions is, well, you add accelerators or strength-enhancing admixtures, and within that category, there's a newer sort of animal there, which is nucleation seeding, and one of them is CSH seeds, and that's what we're going to talk about here. So before we go there, if you just take a quick look here at the scales that we're talking about here, you have the macro scale, which is your concrete. Then at the micro scale, you have cement, which is these are micron-sized particles with D50 values of 10 to 20 micron. And then you have the nanoscale, right? I don't have a picture for nanoscale here because you can't really see it, but I'll promise you at the end of the presentation, we'll show you some work which is in progress where we're trying to look at these seeds with TEM. Okay? And since we're very short on time, we have only 12 minutes, I'm going to skip some of the micro stuff because I want to go directly to the seeds part. So some of this work is related to Raman imaging, and I think we don't need to spend too much time on it, but what I really want to say here is that with one of the techniques we've been developing in the group, you're now able to exactly quantify all the individual phases present in cement. So you can get all the way from halite down to quartz, which is an impurity at the end of 1%. And not only that, you can also get what we call is the size and shape distribution of these clinker phases. So you can now get with these very high resolution images. Each image has about 250,000 pixels. You can get what we call phase-specific particle size distribution. So instead of having a single PSD for your cement, you can have a PSD for every phase. You can have a PSD for halite, PSD for quartz, PSD for calcite. And this could be very interesting considering that in the type 1L cements, where you have a variety of limestone additions, you could have different limestone sizes in those cements. You can also look at other things such as the aspect ratio, roundness, and so on. And we did all this, and we actually did a study where we could find you can use this information to start to predict 3-day hydration of cements. But anyway, I'm going to spend just a quick minute on it and visualizing these as M&Ms. And you can start to develop this composition size quotient where you take the composition and the sizes of individual phases and you start to predict cumulative heat. That all being said, this talk really is about these nano-sized CSH seeds, and I want to talk about them. If you think about the CSH seeds, the prevalence in literature, we really started seeing publications coming out around the 2010 era, and there's about 50 to 60 papers in the last year. And to really understand this data, we should normalize it with the overall publications because the overall papers also are increasing, right? The academics and researchers are pushing out more and more papers. If you search in Scopus with the publication with the word cement, we have about 30,000 publications in the line. This continues to grow. So do a fair comparison, you should normalize the data. So we divide the CSH publications with the cement publication, and you see a small increase. They now take about 0.2% of the publication. And incidentally, that also correlates with the dosage that you can recommend it for these seeds. Now, what happened in 2010? Well, we don't know, but I think one interesting thing is that there's a patent come out which talks about these hardening accelerators, and I think there was some papers in 2009, 2 key papers that took it, but they did not use the word CSH seed, they used the word nucleation seeding. All right, so the research objectives here is we want to take a commercial product, which is a Master X seed product, and see how can they influence hydration kinetics, what's their impact on strength and porosity, and what new insights can be obtained. The goal here was essentially the Illinois Department of Transportation wanted to open their highways and bridges early to traffic, and they want to see if the early strength can be enhanced, and we said, let's try these seeds. So we did a bunch of lab testing on the paste and the concrete scale. On the paste scale, we did the usual suspects in terms of techniques, and at concrete scale, we again did some of the usual suspects, but then we also did actual feed implementation to really see performance in the field. If you look at the kinetics with isothermal calorimetry at different dosages, you clearly see that as a function of the dosage, you see a slight acceleration. If you look at the cumulative heat, there's also a proportional increase in the heat. If you look at two different admixtures, these are the two products that we use, the 44 and the 55, and here also you see a slightly different trend. One of them actually accelerates and one of them slightly retards the reaction. And what we have kind of figured out so far is it also is very much dependent on the amount of PCE and the nature of PCE that is present in these seeds, because too much PCE can cause that retardation. That all being said, if you look at the cumulative heat for both the systems, it actually increases the heat for both of them. So it just depends on how much you care about the set times. If you look at the strength, we generally see an improvement on the order of 20 to 30%. If you look at the porosity, that's the other part, which is something new. We have reported the porosity also starts to decrease. However, after a certain dosage, after 1–1.5%, the gains become marginal. Then we start looking at the microstructure refinement. Then we look at different cases. We have the 100% OPC and the OPC and fly ash. And in both cases, at a 2% dosage, you do see a reduction in porosity, which means not only have a strength gain, but the microstructure is getting refined. Then we did some little bit of advanced analysis here. We took this technique called laser profilometry, and we measured the surface roughness of these samples. And here, something interesting came out. What we're able to see is that we measure certain parameters, right? For example, this is SPC, which is the surface peak curvature in micrometers, and a higher surface peak curvature looks like this on the right, and the lower looks like this. And what was interesting here is as you increase the porosity of a system, the peak curvature also increases. The systems become more and more rough. And if you look at open porosity and correlate that with the, this other parameter called SPD, which is the surface peak density, how many peaks you have when you map this area with a laser, that also, as your porosity increases, that number becomes low. Okay. And what that really means is that by adding these seeds, not only we see the reduction in porosity from helium pycnometry, but also when we do laser profilometry, we start to see a change in the microstructure, which points towards better porosity. So with them say, okay, we have all this data, why don't we try to correlate it and see what we get? So we take different factors we did for concrete as well as cement paste. So the top row is from the lab, so we see a very nice correlation between the total mass loss coming from TGA versus compressive strength. And this is well known, right? The more hydration products you have, the higher degree of reaction, and you'll have a higher strength. If we take the formation factor, also measured via electrical resistivity, there also we see a decent correlation. With open porosity, again, as you reduce the porosity, you get to about 5% or so. Again, your strengths are pretty high. And finally, from the field, we see this interesting kind of a nonlinear trend, because in the field mixes, there's a lot of things, I should say, there's a cocktail of admixtures in the field mixes as opposed to what we use in the lab, and we see this kind of a nonlinear trend where, again, the CS seeds tend to be shifted to slightly to the right. Okay. If you look at this formation factor versus compressive strength data, I think this is kind of fascinating. Again, the lab data, we see a very sort of a linear trend. But if you look at the field data, this is kind of all over the place, right? And our hypothesis of trying to understand this is because if you look at the individual points, they have somewhat of a nonlinear exponential trend. And the reason is that because all of these mixes are slightly different. And this is what something you have to be careful if you're going to use formation factor to kind of use as a proxy to predict strength. You have to be careful because depending on the pore solution, resistivity, and the kind of ions you have, these trends will become nonlinear. But if you are in the field conditions, in the lab conditions on the left, everything is well controlled, you only have one kind of mix, then you actually get pretty linear correlations. So in the end, we convinced the Department of Transportation, okay, well, this is some promising results, why don't we try implementing the field? So we did this in a field, in a box culvert in the town of Armstrong, and there also we actually see pretty interesting results with the CSH seeds. You do see a bump in that early strength, and this is exactly what we wanted. So I think these admixtures could have a potential wherever you need that early strength, and especially in cases where your early strength is low, when you have high SCMs. Okay, I promise that we'll find some pictures of how these seeds look like. So here's some TEM images of these seeds. The nice thing here, as you can see, when you make these seeds in the presence of PCEs, the polycarboxylate ethers serve as a suspension medium to really disperse them very well. So you can see that almost 100 nanometer size seeds are well dispersed, and there's no issue of agglomeration if you try to do through a top-down approach. And this is why these have been quite successful, even at a commercial scale. So what we're thinking now, I told my student, well, we tested a commercial product, it works quite well. Why don't we try to make it on our own in the lab and see if we can tune the behavior and make it work for other mixers? And that is something we're working on right now, and I think there could be a lot of potential there for making seeds tailored towards your application, because now we have a variety of mixes or cements in the market. So if I were to conclude what we have talked about here, CSH of seeds, they affect the kinetics depending on dispersion medium. Excess of PC may cause some set time retardation. Based on helium pycnometry and laser profilometry, we now do report evidence that CSH seeds actually do refine the microstructure. I think this is very important because now we have an actual impact on durability. And finally, we were able to do a field implementation of these seeds, and the future work, I think, which is work in progress now, could be to synthesize these seeds in the lab, and people have been doing that also in the past 10 years, but then fine-tuning them to a specific application or even performance, right? And again, this is the kind of final schematic we're coming up with. With the seeded mix, you not only see increased hydration, but you also see a defined microstructure where the top area here represents the data we get from laser profilometry, okay? So with that, I want to thank my research group and specifically acknowledge the student, Faisal, a PhD student who led this work, and I want to thank our sponsors, and I'm happy to take any questions.